Welcome to the most comprehensive tutorial on hybrid knowledge graph RAG. So today we are going to explore a revolutionary approach that combines the power of Neo4j graph databases with vector embeddings to create a RAG system that goes far beyond traditionally similarity search. So what makes this system truly powerful is how we unite the power of vector similarity search with the graph traversal through Cypher queries. So together we will explore over 11 advanced graph traversal techniques, starting from multivector chunk queries to build exceptionally intelligent RAG system capable of delivering precise, targeted answers to even the most complex and nuanced questions. So in the video description below, you will find the GitHub link to download the complete repository. So this gives you a really fully functional Python project that you can use immediately with Docker, integrating Neo4j. Everything is pre-configured and ready to run, and no complex setup required. Before we dive into the technical details, let me outline how this tutorial is structured. So we'll be taking a systematic approach that builds your understanding step by step. So the tutorial is divided into two main parts, starting from the ingestion process and then moving on to see in detail the hybrid query RAG part. In the ingestion process, we will see how to transform raw documents into an intelligent knowledge graph with strategic vector embeddings throughout the structure. Learn to extract entities and relationships per system in the GraphDB and create multi-vector embeddings for similarity matching. In the second part, we will explore the query techniques. We will understand how hybrid RAG works by combining initial vector search and then expand with 11 different advanced graph traversal algorithms. Start with vector similarity search, then expand results using those sophisticated techniques. From basic breadth first, depth first search, and many others that we will see one by one. Each algorithm actually targets specific needs: broad context discovery, deep relationship exploration, or AI-filtered optimal paths. So as you can see here on the slide, there are 11 advanced techniques we will explore in this tutorial. We will dive deep into each one, uncovering the concepts that make them extremely powerful and sophisticated. Together, we will build Python scripts with comprehensive code overviews to implement these algorithms. So the first one is the Context-to-Cypher. It represents actually a revolutionary breakthrough in graph traversal by using the large language model to dynamically generate custom Cypher queries based on query context and initial results. Unlike traditional fixed algorithms such as BFS or DFS, it intelligently analyzes what information is missing and creates sophisticated database queries to find precisely what's needed. We will see the k-hop limited BFS that systematically explores the graph breadth first hop to a configurable maximum of k-hops, ensures comprehensive local traversal without overwhelming depth. We will see also the same with the LLM predicate filtered. Actually, it improves the k-hop BFS by using an LLM to choose the most relevant relationship types at each hop, depending on the user query. We will see the DFS, that is actually, it conducts a deep first traversal down, relationship chains up to accept depth before backtracking. It's ideal for uncovering deep, multi-step reasoning or hierarchical structure. Also, to the DFS, we will apply the LLM predicate filtered at the same way of BFS. We will discover also the uniform cost search, the UCS, that actually apply a Dijkstra's algorithm over semantic embeddings, treating edge cost as cosine distance. It guarantees discovery of nodes in order of increasing semantic relevance. The same, we will apply the LLM predicate filtered. We'll dive into the A-star search heuristic that extend the UCS by introducing a heuristic based on the query embedding as a goal. So it balances the cumulative cost from seeds with estimated remaining cost HN toward the query. We will see later in detail. The same, we will also apply the LLM predicate filter also to A-star search heuristic. We will discover also the beam search over the graph that performs a layer-by-layer exploration like BFS, but retains only the top k-scoring nodes per depth. It controls memory and latency by pruning lower-scoring branches. And also here, we will see how to apply the LLM predicate filter also for the beam search over the graph. Before diving into the technical implementation, let's understand the fundamental architecture of our hybrid knowledge graph and how different node types work together to create a powerful retrieval system. At the core of our architecture are document node. You can see here all those nodes with a label document actually represent the initial chunks created by the semantic chunker. These nodes serve as the primary entry point for similarity search, okay, and form the foundation of our retrieval system. So each document node contains primary text property, this one. The text property holds the original textual content from the semantic chunking process. And then we have some multivector properties. So there are additional properties that provide alternative representation of the same content to maximize their retrieval effectiveness. We have, for example, translation, translated version for multilingual scenarios, hypothetical queries that generated question that this chunk might answer for the RAG similarity search is really powerful. We can have a summary, condensed version of highlighting key concept, topic keywords, or many others that depend on your specific need. Each of these properties require its own vector embedding to enable multivector similarity search. So this multivector approach dramatically improves retrieval recall by matching against different semantic representation of the same content. So the second layer consists of entity nodes. All the other nodes, that is not a document, as you can see here, they are all labeled with entity. They are sophisticated graph elements extracted from document nodes using LangChain's graph transformer. These nodes represent concept, people, organizations, events, and other meaningful entities discovered with the text. The key concept of entity nodes actually are, first of all, they are unified labeling. All entities share the common label entity while maintaining specific sub-labels like person, organization, and others. Rich properties. Each entity contains domain-specific properties that can also be embedded as vectors. And interconnected structure. So entities are linked to each other through meaningful relationship like this, as you can see here, that preserve actually the semantic context. Okay, each relationship has different property. And also we can create plain text property with the specific embedding. So we can also perform some similarity search through the relationship. We have the mention relationship, that is a standard in the LangChain extraction, and is the critical actually bridge between the document and entity nodes. When we say a document mentions an entity, we mean the entity was extracted from that specific document chunk. The entity has a contextual relevance within the document's content, and the relationship preserves the source-to-concept mapping for citation and provenance tracking. So this relationship enabled system to start with the semantically relevant documents node, navigate to related entity nodes via mention relationships, and explore broader context through entity-to-entity relationships. So the true versatility of this system comes from the ability to create vector embeddings for document properties, as we saw before, so with multiple representation, entity properties, so each entity also has different embedding. We decide which embedding we want for the specific entity. We will see later how to use the parameters to create the embeddings that we need. And also relationship properties, even the relationship themselves can contain embedded properties. So the ingestion process follows a sequence of distinct steps that transform raw documents into knowledge graph with multiple vector representation. Each step builds upon previous one, creating a comprehensive system that preserves both semantic meaning and structural relationships. For our tutorial, we will use a series of documents about Albert Einstein, taken from Wikipedia, just for example, which you can find in the docs folder. So talking about the first step, the system actually performs comprehensive initialization, including session tracking reset, environment setup, Neo4j connection, LLM configuration. The step 2 Documents are loaded from the configure source directory and chunked using semantic similarity analysis. Unlike a traditional text splitting, this process identifies natural breakpoints where semantic meaning shifts, so preserving the contextual coherence within each chunk. The step 3 is the graph structure extraction. Actually, the LLM power transformer analyzes each document chunk to extract entities, relationships, and properties. So this process identifies both explicit and implicit connections between concepts, creating a rich graph representation that captures the document semantic structure. In the step 4, the extracted graph structures are persisted to the Neo4j database with comprehensive metadata and source tracking. So the system maintains relationships between original documents and extracted entities. So in the step 5, the vector embedding creation, actually multiple vector embeddings are generated for node and relationship properties using embedding model services. In our case, we are going to use OpenAI with intelligent filtering based on configuration parameters that specify which node labels, relationship types, and properties to process. So the system creates both embeddings and corresponding vector indexes in Neo4j, enabling efficient similarity search across the graph structure. The last step is the document node enhancement, that actually custom properties are added to document nodes using LLM-generated summaries and analysis. So these properties create additional vector representation that capture different perspectives on the same content. In our project, you can find a files called params, and it helps us to understand how we can set our project and which are the core technical capabilities, okay, that we can configure. So actually, the system allows parametric configuration of information extraction behavior and the creation of nodes and their relationships. So we can either let the LLM freely create node labels and relationship, or we can specify them statically for precise control. So let's walk through each capability and see how it works in practice. First, let's talk about entity extraction control, essentially. Who gets to be in your graph? So you have two main approaches here, and the choice depends on your specific needs. So when you want precise control over your knowledge graph structure, you can use the predefined node type. So you set use allowed nodes here to true and define your allowed nodes in this part. This is a list with the specific entity types like a person, scientist, and you can see here you can find a lot already configured. So during graph extraction, the LLM only creates nodes with these exact labels. So any entity not matching these types gets filtered out. So this approach is perfect for standardized data processing compliance requirements, giving you consistency with the same entity types across all the documents. So compliance that meets regulatory requirements for data classification, performance benefits with faster queries using predictable schema, and easy integration with the existing system. On the other hand, when you want the AI to discover entity types dynamically, you set use allowed nodes false, like as default here, to let the AI decide, and the base entity label to true to add universal label for optimization. So here the LLM actually analyzes each document and creates appropriate entity types. So the new entity types emerge naturally from your content, and the system adds a universal entity label for optimization. So this flexible approach is perfect for research documents, exploratory data analysis, and diverse content, offering flexibility that adapts to any domain, comprehensive capture of all information without pre-filtering, and scalability that works with diverse document collection. So now let's move to relationship schema management, how things actually connect in your graph. You can define the connections between your entities in several ways. For controlled relationship types, you set use allowed relationship true in this param and define your allowed relationship list with categories like worked at, collaborate with, born in, died in, and many others. The system passes these constraints to the LLM, and only relationships matching these types get created, ensuring consistent relationship vocabulary across your graph. For example, In biographical documents, you get standardized relationships like born in instead of variations like birthplace of or originated from. It's a way to standardize the relationship creation. So for even more precise control, you can use the granular relationship control by setting use relationships tuples to true, okay? And defining allowed relationships tuples with specific combinations like a person worked at organization or person, spouse, person nationality, country. The system validates not just the relationship type, but the exact source relationship target combination, providing data quality that prevents impossible relationships like building married to person or something strange like that. So property engineering is where the devil's in the details. How you extract and manage entity attributes. For node properties configuration, you have three options. Set the node property equal true. To extract all properties the LLM finds, set it to a specific list, add property configurations. This parameter controls what attributes get extracted. With true, the LLM extracts all available information like birthdays and description, and with false, entities have no attributes. For example, for a person like Albert Einstein with the node properties true, you get name, birth year, nationality, profession, and what they are known for. For relationship properties, you typically set relationship property description, this is a standard, to add context to relationships. So each relationship gets a descriptive property explaining the connection, like worked at, becoming, employment at Princeton University from 1933, 1955, for example. So this gives you context to understand the nature of each relationship, temporal information about when relationships started and ended, and searchability to find relationships by their description. So the multivector embedding architecture is your smart search engine. How you make your graph searchable through multiple dimensions. For selective node embedding, you configure filter node labels to index, for example, with values like document, concept, person, okay? And filter node properties to index with the system checks if a node type should be embedded. Only specified node types get vector embedding, okay? And only specified properties get embedded, which saves cost and storage, enabling semantic search. For relationships embeddings, you set filter rels property to index in this part. For example, you have description also here, and filter rels labels to index all, okay, to process all relationships types. So the system embeds relationship description in the method is collect relationship properties to embed. So the automated multivector properties features is particularly powerful. You configure document multi-vector properties with entries like a property named HYP queries with a prompt to create 3 hypothetical queries that users might ask about this document. Each document gets hypothetical queries, in this case, for better query matching, and translations enable multilingual search. For example, a document about Einstein's theory gets hypothetical queries like what is relativity, Einstein's contributions to physics, and so on, and Italian translation. So this provides better matching because hypothetical queries catch different ways user might ask, multilingual capabilities for searching in any language, and it's completely automatic with no manual work required. You define vector search configurations here with tuples like a text document, hype queries documents, to search text embeddings in documents, to search hypothetical queries in documents. So you also set top K initial 10, in this case, for initial search results, and top K traversal 100. So text processing limits include also max embedding text length. So finally, advanced customization lets you adapt to your unique requirements. For custom extraction prompts, you set use custom prompt to true and define your custom prompt with your specific instructions. This replaces the default extraction logic with your custom prompt gives you complete control over what gets extracted and how, and is perfect for specialized domains and unique requirements. So for vector search strategies, you configure graph traversal method with options like beam search, Context-to-Cypher, and many others. And as I explained before, we have in this tutorial 11 different graph traversal texts, but of course you can customize, you can add more, you can experiment as you wish. And you also activate initial vector search true. This is important actually, because if it's false, actually it skip the initial similarity search through the documents and go directly to graph traversal method. Okay, if you activate this, you get a solid base from the documents chunks, and then you expand with the graph traversal, and we will explore one by one later in this tutorial. So the key is to try different configurations with your documents and see how they affect your results, starting with the defaults and gradually customizing based on your specific needs. Now let's dive deep into the code architecture with a comprehensive review of how the various classes and methods work together in the ingestion script. So the file is ingestion.py. Let's start with the knowledge graph ingestion class. So the core ingestion system is built around a comprehensive class that manages the entire pipeline from document processing to vector index creation. So the step one is setup environment. This method actually implements a failed test validation strategy that checks all required external dependencies before beginning the ingestion process. The approach prevents partial system initialization that could lead to inconsistent states. So the validation process includes API key verification, database connectivity, and permissions checks. The step two is actually check Neo4j version. It addresses actually critical compatibility issues between different Neo4j versions because we are using many different features, particularly regarding vector index capabilities. The system dynamically adapts its vector index creation strategy based on the detected version. We have the other method that is load from docs folder. Okay, so it's going to load the documents from this folder. And actually the semantic chunking, so the system uses vector embeddings to identify natural breakpoints in text where semantic meaning shifts. So rather than relying on arbitrary character count or sentence boundaries. So multiple algorithms are available for determining chunk boundaries. So the text splitter is the semantic chunker that is initialized here in the initialize embedding services. And here we have from LangChain our semantic chunker with some parameters. We are using from params, the type percentile actually determines the method for identifying breakpoints in semantic chunking with options including percentile, standard deviation, and interquartile. The semantic chunker breakpoint threshold that is default on 95% that sets the threshold value for semantic chunking breakpoints. For percentile, these represent the top 5 of discontinuities where higher values create fewer, larger chunks. We have the semantic chunker mean chunk size that is actually set in params for 2000 for default, establishes the minimum size for any semantic chunk, preventing creation of a very small chunk that lack context. The next step is extract graph from documents, this method here, that actually use the self-transformer convert to graph documents. And this is a method from the LangChain transformer. So the LLM-based graph extraction process implements sophisticated natural language understanding to convert unstructured text that we got from the semantic chunker into structured graph representation. So actually is responsible for entity recognition and classification. So LLM identifies and categorizes entities based on configurable schema, including name entities, conceptual entities, document-specific entities, It also provides a relationship extraction. So the system identifies and classifies relationships between entities using semantic analysis, relationship from sentence structure, and coreference resolution, like linking pronouns and references to their entities. So both nodes and relationships are enriched with the properties extracted from the source test, including descriptive properties, attributes, characteristics, and metadata, temporal properties, time-based information and sequencing, quantitative properties like numerical data and measurements, and also schema validation. Some important key parameters from Paras PY we already discussed before is allowed relationship, use allowed relationship, allowed nodes, use allowed nodes, and so on. So we can get to the next step, that is create vector embeddings. This is the really important step that actually is a vector embedding strategy. Is a pipeline that implements a multi-layered approach to creating searchable vector representation. Here is the step-by-step, the pipeline. Rather than embedding all properties, the system uses configurable filters to determine which properties should receive vector embeddings based on content type, where text properties are prioritized over numerical or categorical data. So length thresholds that ensure properties contain sufficient content and meaningful embeddings, and semantic value assessment that prioritizes properties with high semantic content. So each property is embedded with additional context to improve search relevance. That's all depend on the parameters that we saw before. Parameters like add vector index, vector embedding dimensions, vector similarity function, for example, that sets the similarity. Let's see, for example, add vector index is here. So if the param is add vector index, we are going to add the vector embeddings directly in the elements. And the vector embedding dimensions here, that is default, is 1536. We can change depending on also on the embedding model that we use. The similarity, the vector similarity function that sets the similarity function for vector comparisons like a cosine or Euclidean, in our case is cosine. Max embedding text length, that actually is 10,000, is the maximum character length for text values to be embedded. And embedding exclusion prefix, actually prefix to exclude from the embedding, the batch size, and we already saw the filter node labels to index, and we saw if this all is going to include all the possible labels, but we can filter, and also for the relationship the same way with the filter else labels to index that we saw before in the params. So the parallel processing implementation uses a thread-pool executor to process node and relationship embedding simultaneously, reducing total processing time while managing API rate limits and preventing resource exhaustion through batch processing and failure isolation. So the next step is multivector document properties. So with this method, we add the multivector to the documents node. This is specific for the document label. This approach creates multiple, this function creates multiple semantic representation of the same content, each optimized for different query types. You can specify in the params, you can define the prompt to create a new vector, to extract a new vector. And for now, we just define the hypothetical query generation, translation, but you can add also summarization or many other technique. We are entering the part 2 of our hybrid knowledge graph RAG journey. After building our knowledge graph with the multivector embeddings in part 1, we now turn our attention to the heart of our system, the hybrid RAG query architecture. This is where user questions are transformed into comprehensive contextually rich answers through intelligent knowledge graph exploration. So instead of simply matching queries to documents through similarity search, our system orchestrates a three-phase process that combines vector search with intelligent graph traversal, creating a hybrid approach that maximizes both precision and recall. So at its core, hybrid RAG query system is built around a singleton pattern, as you can see here, this class, that manages all query operation while maintaining optimal performance through connection pooling and state management. But this is just the beginning. The system implements a sophisticated orchestration layer that coordinates multiple AI services, graph traversal, algorithms, and answer generation techniques. So let's discover the complete architecture through the lens of our Python implementation. The import structure reveals the modular design of our system. We are importing not just basic database, but the entire ecosystem of specialized traversal algorithms. Each traversal method represents a different approach to exploring knowledge graph, and our system dynamically selects the most appropriate algorithm based on the query characteristics and configuration parameters. The environment setup actually implements a fail-fast validation strategy that checks all required external dependencies before beginning query processing. This actually prevents partial system initialization that could lead to inconsistent states. The query processing is a three-step pipeline. The first step is the vector search, the initial similarity-based retrieval using multiple vector indexes to establish a foundation of relevant documents where actually to start. The second step is the graph traversal, and is an intelligent expansion of initial results through graph relationships, discovering additional relevant context. And we are going to set up, to decide which traversal to use in a parametric way. Actually, we can set directly in the main execution. In the main execution, checks actually the parameters graph traversal method and initialize the right class from the import state. And the last step is the answer generation, that is a summarization of all collected context into a comprehensive answer using advanced LLM models. So let's discover the complete pipeline implementation. We are in main. The multi-vector search configuration, actually we can set directly in the params, and this called vector search configuration here. It enables fine control over search behavior through this variable. So this allows the system to search multiple vector representation of the same content. In our case, we are going to use text, that is the original chunks from the semantic chunker, and the hypothetical queries, okay, that we already create during ingestion step. Going back to our query, the phase one, so is the vector search, is executed by search similar documents method, and you can find the method here. The search process actually implements some techniques like multiple embedding properties are searched simultaneously, each potentially revealing different aspects of document relevance. The system implements search by index, and this method constructs index name based on the embed property and target label, following the naming convention established during the ingestion process. Before attempting to search, the system validates that the required vector index exists. This prevents runtime errors, of course, and the search returns comprehensive metadata, including node IDs, text content, source information, chunk details, some similarity scores, and other information. So this metadata is crucial for downstream processing and result implementation. We also implement a result duplication and scoring mechanism in the duplicate and sort result. The process uses node IDs to identify the duplicate documents while preserving the result with the highest similarity score. So this ensures that when the same document is found through multiple vector searches, we keep the instance with the best score. And the results also are sorted by similarity score in a descending order, ensuring that the most relevant documents are prioritized in the final result set. That takes the initial nodes from the multi-vector similarity search nodes and query as parameters and returns additional context node. The architecture also implements sophisticated context combination with intelligent deduplication that is called deduplicate context. And here we go. This is the function that actually prioritizes initial documents from vector search over additional documents from graph traversal when duplicate exists. So these ensure that the most directly relevant documents are preserved. And the function maintains the original order of initial documents while appending additional documents from the graph, then sorts the final result by similarity score. The phase 3 is the last step, that is answer generation with context formatting. Is the final phase that collects the context and generate a comprehensive answer. The method is a generate final answer, and it's here. The system uses LangChain Chat OpenAI, but you can change it with any other model. There is also a context formatting method here, and it removes some useless attribute from the graph traversal. Useless for the final answer for the LLM, but helpful, we will see later, during the traversal execution. The formatting process separates document nodes from relationship nodes, and the relationship nodes contain entity and connection information, providing structure context that LLM can easily process. We have also other important parameters we can set for the query. Other parameters are top k initial. This is the maximum number of results to retrieve per vector search, controlling the rate of initial context. We have top k traversal, is the maximum number of results to return from graph traversal. We also have activate initial vector search, whether to activate the initial vector search phase, or maybe we only have a traversal only query processing, just if we put these to false. And we also have a graph traversal method, that is the most important parameter to specify which graph traversal algorithm to use. It's time to discover the graph traversal algorithm, each optimized for different query patterns. Let's start with the Context-to-Cypher. That is actually LLM-driven intelligent query generation, basically. It represents a really advanced technique by using the large language model to dynamically generate custom Cypher queries based on the context and initial results. Unlike fixed algorithms like BFS or DFS, it analyzes what information is missing because we provide a context and create some database queries to find exactly what is missing from the initial similarity search chunks. So the prompt is composed by user intent, the formatted initial retrieved docs, the graph schema, and the vector indexes list. The second step is generate the Cypher query. So we call the LLM and it generates a Cypher query. And at the end, we have the final answer with a prompt where we put the user intent, the formatted initial retrieved docs, and the node and relationships from the Cypher query. The system combines in the prompt over 20 search patterns as an example, but the system is not strict to follow them. It's just some few short example in the prompt, from the vector similarity to semantic relationship discovering, using all the features from the Cypher, but also from the schema, because as you remember, we integrate many information in the graph and many vector embeddings. The query is going to use also similarity search to get more information. Let's explain how the class is composed. The initialize method is always the same for all the technique, and you can find in query it actually is the traversal graph. So here in the Context-to-Cypher, the traversal graph actually is the method that is going to start the pipeline. And also this class has initial environment setup, like all other class. Setup environment with the same steps. And let's discover one by one this pipeline. We have generate Cypher query, actually generate the query. It execute and it filters some properties. Let's discover the get graph schema. This is the most important in the generate Cypher query. Generate a prompt with different part with the basic schema. So we get the basic graph structure from the graph. The list of the vector indexes that tell the LLM which embeddings are available for the similarity search, to put the similarity search in the Cypher. And we also add many other information. You can see here many patterns to drive the model to create optimized cipher. Actually, is a range from basic vector similarity searches to advanced techniques like community detection, temporal relationship analysis, cross-domain bridging, and other techniques. So the prompt include an example of each one, but we are telling to the model that actually do not copy these examples directly, but use them as an inspiration to craft a custom query that fits the specific context, schema, and information needs of the current request. So after generate the query, we enter the execute cipher query step. This is actually an interesting thing because it demonstrates the sophisticated integration of vector embedding here. So in the query, when we execute the query, we want to know if the cipher, the generated cipher, has some query vector to create some embeddings to put in the execution, okay? So the system automatically detects when vector operations are required, so generates appropriate query embeddings and executes the complex queries with proper parameter bind. So this integration enables the LLM-generated query to leverage the full power of vector similarity search within the graph traversal operation. The next step is the filter properties that removes technical metadata while preserving all semantically relevant information. And the filtering process ensures that embedding vectors and other technical properties are removed from the final result while maintaining all contextual information needed for high-quality answer generation. And another method that actually is clean cipher response. This is a cleaning mechanism actually that handles the complex task of extracting clean cipher queries from the LLM response. The cleaning process handles markdown formatting, explanatory text, and various response format while ensuring that only valid cipher queries are executed. This cleaning actually prevents execution error and ensures consistent query processing. As we saw before, the traversal graph is actually the main function of the Context-to-Cypher and orchestrate the entire Context-to-Cypher pipeline and ensure that each query receives intelligent, adaptive treatment based on its specific requirements. We have also some parameters that we saw before. We have, of course, the model, the top K traversal that is default 100. Okay, that is the maximum number of results. We also have vector embedding dimensions. In our case, is for OpenAI text embedding, ADA, and the vector similarity function that we use that is cosine in this case. Let's see the Context-to-Cypher in action. You try to answer some complex question. If you go to query, you have some query example that I just create from the docs. The docs, as I said before, is some information about Einstein that I get from Wikipedia. The first query, let's try this query. So construct a timeline year by year of every birth and death mentioned for Albert Einstein, immediate relatives, parents, siblings, spouses, children, and grandchildren. Then highlight which of those people were still alive on April 18, 1955. That actually is a complex query. Before starting, let's change in the params, because actually the traversal starts from the initial chunks and we are giving a context to the model to create a cipher. But if we get too many documents in the first step, maybe it doesn't create any cipher. It just return null because it get enough information to answer. Now the top K initial is 10. It's too much. We try with 2 and see. We try with 1 and see what kind of is less information. We see what kind of cipher it create for us. I'm really curious about that. Let's start. So we already set the graph traversal method Context-to-Cypher. And let's start the script. No. Here we go. We get some logging. The phase 1, we are creating hybrid RAG query instance. Is the vector search. We found just one result because we put just maximum 1 top K. We get this with this similarity, early life, this is trimmed chunk. And we're getting to the phase 2, that is graph traversal analysis. We didn't get anything because he already got in the first chunk. But I'm curious to see. Oh, okay, create this complex query, but we got an error. Query cannot conclude with call master, return close or finish close. Okay. Let's try again. Anyway, it gave us some information because the chunk that we retrieved was good. Let's try again, Python. Let's try to change the top initial. We give more. Let's see what happened. Okay, we got 2 documents. Initialize the Context-to-Cypher. I hope this time we create a simpler query, simpler cipher, so we don't get the error again. Actually, we have to, okay, we got some relationship. So the cipher, the execution works. So this is the first chunks, and then we got some relationships. Okay, the relationships actually is the part from the cipher, and this is actually the final query. Match the person parent of, or return the element, union sibling of, married of, and also parent of. That's really smart, yeah? That's really smart because actually the LLM from the schema, he tried to get all the relationship between Albert Einstein and all other person in the documents. And he got information. He got Hermann Einstein, that is an entrepreneur, the nationality, when he was born, when he died. Pauline Koch, the occupation is pianist. Pauline Einstein. If you are sharp enough, you will have noticed that essential information was missing from the previous results. Specifically, I'm talking about the relationships of the nodes with other nodes acquired from the cipher query. So the cipher returns node and properties, but the relationship were lost. For example, if a node representing Einstein wife provided the properties, the spouse of relationship was lost. So I don't want to ask the LLM to include dynamically because it's going to overwhelming the cipher generation, but I want to do it statically, okay? So I added a function that adds all the relationship present in each node as a sort of property, a string that combines the relationship types with a specific node ID in order to provide greater context to the results. So the function is called add connection node, and for each node it adds connection to other nodes, except for mentions type connection that we never need that. We can find here, I added just right now, add connection to node, this one, and it's quite simpler. So from the results, this is an array of nodes from the cipher query, we add connection. We call connection actually our relationships. We create a copy, a deep copy, and the node ID actually is the name of the node. It's like a node name. We call ID, but actually it's the name. It match all the connected node where element ID, node ID, and type is different dimensions, and return the type, the relationship type as a relationship type, and coalesce the connected ID, element ID as connected node ID. Okay, so give back the relationship type and the connected node ID, because in my string I want to create like a connection node ID, connection node ID is going to be spouse of Albert Einstein, brother of Albert Einstein, or friend of another person. That's dependent on the specific query. But getting all the relationship around the node give the full context, the full nature, the full characteristics of this node, of this specific node. And we are going to concatenate here and give back the enhanced results. Let's see in action. Let's see if it improve our answer. But first of all, in query, we add also this part. For each person, give the relationship to Albert Einstein. Okay, let's try. Oh, we launch the query. We get the first chunks with the vector search. We fix the top key to 2 as before. Also give us which doc from which document. Here we go, beautiful. See, look at here. The first 2 chunks and then all the relationships, okay? Actually, we can call traversal graph elements. Relationship is not quite good here because this is the relationship that we call connection actually. Yeah, that's the element, the properties and the connection. So Hans Albert Einstein was born in Bern, was Switzerland, parent of. Actually, we have, okay, sibling of Edward Einstein and all information. So this is the real the real node with full information. That it's really important. And at the end, let's see. Here we go. The timeline of birth and death. Look at that. Hermann Einstein born. It's the Albert's father. We didn't have this information before, remember? And also when dies. Pauline Einstein, Albert's mother. That's really effective. Okay, we lost all those information before because the cipher just returned the node, not the relationship. We added with this function. I feel really satisfied of this feature. Let's go to the next graph traversal technique, that is K-hope limited BFS. Actually, we are going to explore together the K-hope, but also we'll see the depth limited DFS, and we compare to each other. We compare to see the differences, and we're going to explore all these techniques together, these two techniques together. So the K-hope limited BFS represent a systematic approach to graph exploration that balances comprehensive discovery with computational efficiency. So this method performs control expansions of search result through breadth-first traversal, implementing sophisticated limiting mechanisms to prevent exponential growth. So we start from a source node, we go to the first layer, we explore all, second layer, we explore all the nodes, and so on. So the output is going to be 0, 1, 2, 3, 4, 5, 6, 7 with this order. Let's see the difference with the DFS. Before we dive into the K-hope implementation, let's take a moment to understand why we have different traversal algorithms and when to use each one. Think of it like choosing between exploring a city by walking through every neighborhood systematically versus following one interesting street as far as it goes. So the BFS is like being methodical explorer. You start at your current location and visit every nearby place first before moving to the next block. It's systematic and you're guaranteed to find the shortest path to any destination. In your knowledge graph, this means BFS will discover all the immediate relationships around a document or entity before exploring more distant connections, like a bigger circle around the starting node. But the depth-first search, on the other hand, is like being a detective following a lead. You pick one interesting path, okay, and follow it as deep as it goes. Maybe you start with a person, then follow their employer, then their employer's founder, then their founder's education, and so on. So you're building chains of relationships, uncovering complex stories and causal sequences that might span multiple steps. So the direction is from the node to the last leaf, okay? So we start from 0, we explore 1, and then go to 4, and then we go back to explore node 1 and 5. So first exploration, second, and we go to node 2 until 6, we go back, 3, 7. So the output is going to be 0, 1, 4, 5, 2, 6, 3, 7. We explore in like a parallel circular way. We explore following a path. As you can see here, this is the exploration of the BFS, initial node, hope 1, 2. We can set the max hopes, okay, and the max node. In this way, we explore only 2 layers to hope, 1, 2. But the max node stops at 7. So the output is going to be 1, 2, 3, 5, 4, 5, 6, 7. That's quite simple concept. But for the depth limited DFS, we use another strategy. We set the max node 9, max depth 3. We start from the initial node and we go to 1, 2. We don't go to 3, but we go to 4, 9, 10. We go to 1, 2, 5, 1, 3, 6, 11. And the last one is going to be out of our search. So the output is 1, 2, 4, 9, 10, 5, 3, 6, 11, okay? And as you can see here, for each technique, we have an evolution of the technique, adding a LLM predicate filtered. That's quite simple concept. We don't accept all the node, but we filter the node depending on a specific relationship. That's quite interesting. Actually, I didn't read this technique anywhere. I created from scratch, just an intuition. The intuition is that why we have to accept all the node, just get only the node that have specific relationship. But what kind of relationship? Who decide which relationship? Is the LLM. So the LLM in this case has like a smaller responsibilities. It doesn't create a cipher query like the beginning, but it only filter the relationship. So we are going to give a prompt to the LLM and say, okay, you have all this relationship. This is the user query. Tell me which relationship is it match with the user query, okay? And we're going to filter out only the node after the cipher, after the algorithm, the KOP. We filter out all the node that doesn't match with the relationship type chosen by the LLM. And I think it improves a lot because actually it reduces the tokens for the final prompt and give more specific answer, more precise and contextualized answer. We are going to apply this LLM for each technique, also for the DFS. It's the same. We will see later that we have a script file for each algorithm. And for the LLM predicate filter, actually, we apply on top of the algorithm. We apply a class that actually decide which is the filter and pass the filters as parameter to the depth-limited DFS query. Also, going to see this other technique later, but we apply the LLM also to the others. Okay, we get a little bit far. Let's get a step back. So we were comparing the BFS and DFS. Actually, what is fascinating is that both approaches have the same time complexity, okay? They visit the same number of nodes and relationship in the worst case, but they use memory very differently. BFS needs to remember every node at the current level before moving to the next level, as we saw before, but which can hit up more memory quickly. DFS only needs to remember the current path it's exploring, making it much more memory efficient. So when do you choose which approach? If you are trying to answer a broad question like, what do we know about artificial intelligence? Well, maybe BFS, because it'll give you your comprehensive coverage, all the key concepts, researchers, applications, and techniques at each level or relevance. But actually, if you are trying to trace a complex chain of influence, how did early cybernetics research influence modern machine learning? Something more specific. You want DFS because it excels at following those deep multi-step connections. In our system, we use both just for a didactic purpose, and I really want that you understand deeply both solution and you choose strategically depending on your project. Let's discover the code of K-Hope limited BFS. You can find it in the PY file, this PY file, and it's all managed by this class. Actually, the initialization established the core parameters and set the services and everything the same way we saw before. And we have some important parameters that is max hopes, is the max number of layers that we're going to explore. We have also max neighbors per node, is maximum number of neighbors to consider per node. Max total nodes, and this is true. We remove mentions nodes because actually they are related to the initial documents we don't want to consider for the extensions of graph. And this is the rel type filter, is the list of relationship types actually that we will use to apply the predicate filtering by the LLM, and we will see for the next step. Now we don't apply any filter, we just perform free K-Hope limited BFS. The main method is traverse graph, like others, and actually the method orchestrates the entire BFS process. As you can see here, extract node IDs, perform K-Hope BFS, and filter properties. The system begins by actually extracting the node identifiers from the initial document results, then performs the core BFS traversal with configured limits. The process includes intelligent filtering and removing the noisy mentions that I told you, and property filtering. Let's see perform the core algorithm actually. This is extract node that's actually just take the IDs from the initial relevant docs from the multivector initial search. Actually, it's the starting point for expanding the K-Hope. Let's see the perform K-Hope BFS. And that's actually a classic graph traversal that enhanced with intelligent limiting mechanism. The algorithm maintains a visited set to prevent cycles, a queue for level-by-level exploration, and a discovered nodes list for result accumulation. So the traversal process includes hope level tracking, neighbor limiting per node, and global node count limits to ensure predictable performance. The system enriches each discovered node with metadata included hope level, discovery path, and relationship context for enhanced answer generation actually. We have the get node neighbors, that is an essential part for the algorithm, this part. So actually we get we get the node name ID property that actually is the name of the node, and then we get the neighbors. The neighbor discovery mechanism actually implements filtering strategies that adapted based on traversal depth and configuration. For the first hop, the system explores, as we saw before, all the relationship types to ensure comprehensive initial expansion. So this is the expansion cipher, okay? Match the central relationship neighbor where element D is the node ID that we are passing, and the relationship type in rel type. So it actually returns also the relationship type. At the end, we have the output actually explain the node, including all the property here, the labels, and also the relationship types. We want to know the relationship types and the name of the connected node with the specific relationship. Let's see it in action. Okay, so we are going to use a different query than before. We use maybe the second one. Two of Albert Einstein children pursued medical studies but met very different hands. Identify them, specify where each studied, summarize the health condition that shaped each life, and state whether Einstein ever reunited with them after leaving Europe. Okay, let's try. Hurry, Python. Query.py. Of course, in params, I changed the graph traversal method with KOP limited BFS. We are starting with we put 3K initial. No, let's keep it 2. It's okay. I don't want too much context. Let's see if the exploration is enough from 2. If not, we will get too many nodes. Here we go. Let's see. So we have all the initialization here. We have all the logs for the exploring from hop 1, hop 2. Found the neighbors for each node using all relationship. We don't have any filter. And here we go, we get this is really fast because there is only one LLM API call at the end for answer generation. All the rest is just a query to database. We get the first 2 chunks, and then additional nodes from graph traversal. I changed it from, remember the relationship, I changed it, and this is the correct key. We get for each node, we get the labels that explain what kind of node it is. The property ID is the name, actually, that represent the identity card of the node. The relationship type born in, okay, related to the name Hermann and Einstein, okay? So actually, Hermann Einstein born in Buchau. Yeah. And the same here. Pauline Koch, parent of Maria Einstein. And here we go. Here we have a really specific connection with the relationship type. Remember before we added all the relationship around the node except for mentions, because the cipher generated from LLM doesn't include the relationship, and is going to be too difficult to include the relationship the query. So we added systematically for all the relationships. In this case, we just add by ourselves. We just add with the cipher that we saw before. And here we go, we get all these nodes. Actually, there are too many because the max number is 100. We can anyway cut it. And here we go, we have the final answer. So it works pretty good. So let's filter out something not interesting for the user query, okay? Applying this method that is the predicated LLM filtered. Let's see how the LLM choose the correct relationships. But first, let's discover how the filtering is working. If we go to cop limited pred LLM, this one, we'll see that to create the filter, it's quite easy, actually. It traverses the graph, okay? Actually, it's calling the cop limited BFS that we already explained, is importing the normal class without filtering, and is giving the parameters selected relationship as a rel type filter, okay? So just before calling the class exactly at the same way we did before, we just added some selected relationship that they are determined with this function. Before calling the LLM to select the relevant relationship, we get all the relationship types. How we do it is just getting a schema. We match all the relationship from our database, distinct, so unique values, and we just return just a normal list of relationship type. Okay, born in, spouse of, father of, and died, born, and etc. Here we go. We have the selected relationship, and after we just call. If there is no selected relationship, we just perform a normal BFS traversal, exactly like before. So it also depends how the LLM decide. If we go to the prompt, so you can see the specific prompt, relationship selection prompt. So you are an expert graph analyst, given a user query and a list of relationship type in a knowledge graph, you get the user query. A knowledge graph, select the relationship types that are most relevant for answering the user question. Just pretty easy. User query, relationship type list, we give a specific instruction. And also the format instruction here that is we get from the script here. Oh, we also provide a brief reasoning for your selection, so we can understand why you select specific labels, just more information. The format instruction actually is, format instruction. Is it? Okay, is a get format instruction. And we get from is get format instruction. Here we go. Output parser. Oh, okay, it's just a method already included in the output parser. Okay. The output parser from Pydantic output parser. That's quite good because we're using Pydantic for the output. So this is the, let's see, this the parser, relationship selection, and is exactly like that. So this is the types, the schema we want as output. Okay, so this define actually what is in this prompt, what is this format instruction. Is select a relationship and reasoning. So this is a list of string, and this is a string, just a field with a specific description. So let's see it in action. We use the same query as before, so we see also the different. Okay, same, but before. Okay, but I think we didn't change in the param, sorry. So we make exactly the same query as before. We need to specify pred LLM, pardon. Okay, I was thinking, still a lot of nodes. Python query, let's see. Now I hope, okay, here we go. So this is just the list of all our relationship types, okay? The model choose these relationships. That's quite precise. LLM selected 11 relationships types, and it makes sense, yeah? Parent of, studied at, alums, graduated from, is all about the user query. It's all about the user query. This is the reasoning. To answer the query, we first need to identify Einstein children parent of, then find where each person medical studied. That makes sense, yeah? And using those relationships, as you can see, the nodes are less than before. So we much less than before. And we still get the same answer actually. So it makes you save a lot of tokens. And I think is around, let's see how many. I think it's around 30. So we save 70% of tokens, okay? Because we cut 70 nodes, then we just choose 30 instead of 100. Quite good, right? So now let's see the depth limited DFS. We explained the concept before. So actually the difference, the innovation is that it's following a specific path instead of discovering layer by layer. This is the class that manage all. It has actually all same method, setup, initialize, traversal graph. We extract the node IDs at the same way from the initial docs. And we perform what is interesting to discover is depth limited DFS. And we also filter some properties. Actually, filter properties we didn't see before. It's just removing the embedding. It's just removing the embedding, I think. Yeah, remove the embedding because the LLM doesn't want huge numbers, huge amount of numbers. The limited search it create a stack also here. And the type in this case is LIFO, so last in, first out. And this system actually give you the exploration following a single path until the end, until the last lift and go back. So get the node, get node name ID property, get node neighbors. and it applies the max neighbors per node. And here is the core of the mechanism. You remove dimensions and it adds to the visited the neighbor ID and append the neighbor with the depth. This is actually our stack that make the system understand what you visit and how you visit, and actually it actually help you to explore in a DFS mode. And the get node neighbors is also here. We get labels, properties, type, and we have also the score for each one. And here we go. So it's similar to BFS. The only things that change is the exploration algorithm. And we return a series of information about the exploration. So let's try another query. So we go to, let's try third, query 3. So describe the full corporate journey of Einstein. Give its founding city and year, the founder respective roles, industry it served, reason for its move to Italy, the city to which it moved, and the ultimate fate of the enterprise. Let's see, without the predicate filter. Oh, we have to change in params, of course. We change to depth limited DFS. Okay. Python.py. Here we go. Great. So we get at the same weight 100 dot, but in a different order, remember? So the order is giving priority to the path, the initial chunks. We start from these two nodes chunk, document chunk, and we get all these nodes, and we get the final query, the final answer. Let's try with the filter, LLM filter applied. We go to params, we change to other method that is a depth limited pred. We go. Okay, so like before, we get all the list. We just log all the relationship types, and let's see. It shows actually different relationship. It makes sense. Founded, based in, founded by, roll in, produces, expanded, move on, relocated to, resulted in, transformed into. It works quite good. Okay, so we get match. We just get crazy, huh? We get 1, 2, 3, 4, 5, only 6 nodes, really specific, really precise, and we get the same answer, a really good answer. Great. Let's go to the next graph traversal technique. Now is the time of UCS, that is a uniform cost search. Let's understand together how it works. Before we dive into the code and the query testing, let's understand what makes a uniform cost search fundamentally different from the algorithms that we have seen so far. Think of the UCS as the intelligent pathfinder that always chooses the cheapest route to new information, where cost isn't about distance or time, but about semantic similarity. You can understand it just graphically. As you can see here, when we start from the initial node, we are going to explore other nodes, and we actually sum a component of the cost. So the total cost is the one that actually drive the algorithm. Okay, so a traditional graph algorithm actually treat all the edges equally. So whether you're following a relationship between a person or the employer, or between a document and a random keyword mention, each step costs the same. But what if we could weigh these relationships based on how semantically similar the connected entities are? So that's exactly what UCS does. So instead of treating all the graph edges as having equal weight, UCS calculates the cost of traversing each edge based on the cosine distance between the vector embeddings and the connected nodes. So this means the algorithm will prefer to follow paths through semantically similar entities, naturally discovering more coherent and relevant information chains. So here is the beautiful part. UCS guarantees that nodes are discovered in order of increasing semantic distance from your starting points. This means that the first nodes you discover are the most semantically similar to your initial documents. And as the algorithm progresses, it explores a progressively more distant but still relevant information. This is particularly powerful for queries where you want to expand your context in a controlled, semantically guided manner, instead of randomly exploring the graph or following arbitrary relationship types, UCS intelligently navigate towards the most relevant information using the power of vector embeddings to guide its path selection. The question is, what embedding we compare between nodes? You can, from the initial node, we compare the embedding from 1 to 2, from 1 to 3, we calculate the edge cost, and when we go explore the next level, we get edge cost between 2 and 4, total cost, we sum from the previous total cost, so it's 0.4 plus 0.2 is 0.6, and the same from 4 to 10. When we reach a point where a single node, we can reach it through two different paths, actually we choose the path that has the smaller cost. Here, to reach it, we get 0.9, here we get 0.6, so we choose the best cost path. This is actually the logic behind this algorithm. So if we set the max node 10, how we choose the output and the order of the output, it's quite simple. You just follow the cost. I mean, you explore all the node, you start to explore in the node, starting from 2, 1 to 2, we go to 4, 5, 6, 10, 11. And from 1 to 3, 6, 8, 9, 12, 13, 14. But we just take all the node with the smaller total cost. So we are ordering all the exploration, all the node exploration from the smaller in a ascending way, and we decide, we choose that the first 10. So 1, 3, 2, 8, of course, 1 is the first, 3 is the small, is 0.1, 2, 0.2, 8 is also small, 0.25, and we just cut the bigger total cost, like 1.45, 0.65, and we keep just the smaller one. That it means that there's better similarity between the embeddings. But what embedding we use? We will see later in the code that actually we use all the embedding that are available inside the properties. You remember, we create some embeddings. We create embeddings, for example, for the initial chunk with the text, with the hypothetical queries, with description. So we have many different embedding, and we just concatenate all together. So we create one single embedding, and we use also some padding techniques to have all the concatenated embeddings with the same length, and we perform a similarity between them. So let's analyze the code. We get into the uniform cost search UCS PY. We have the same class, the same setup environment, initialize Neo4j connection, the main method that is traverse graph. So we extract the same way the node IDs, and we start to perform UCS from the starting node IDs. And also we have the filter properties that remove the embeddings. Let's see how perform UCS work under the hood. We're starting from the node IDs, from the params. So we create a set of visited node, priority queue, discovered node, best cost, and node metadata. This variable help us to create a representation of the evolving algorithm. So for node ID, in starting node IDs, we are going to iterate, initialize actually the dictionary for node metadata. We get the node embedding batch, so it's a starting embedding. Actually, this helps us to calculate the concatenated embedding, to calculate the edge cost and the total cost. We start this loop while priority queue and discover node are smaller than max total node. This is our parameters. We calculate actually the current cost, we get the current node ID, current level. If it's visited, we continue because we already elaborate. We add to our array visited, and we just keep dimensions. And we calculate all the get node name property. We get the embedding. The embedding actually is calculated in this way. So we get all the embedding, return the properties, and we just filter only the embedding properties. Okay. And we get the node neighbor. So for each iteration, it actually is the priority queue. And we get the node embedding batch, okay, that actually is just getting the embedding of all the neighbor. on the node IDs, on the starting, node IDs. We're getting all the embeddings best for the neighbor IDs to compare and to perform the similarity. For neighboring neighbors, we are going to calculate cosine distance. Okay, we calculate the edge cost. So the new cost is going to be the current cost plus edge cost. And in this part, actually, we are going to track also all the path that lead to this specific node, and we keep only the best path. Okay, actually the path with the smaller cost. And we're going to write on the neighbor info all our information, and also to node metadata. We are going to store the neighbor info. So at the end, we are going to have a representation of this algorithm with all the discovered node sorted by the total cost. We sort here, actually. This is the final part of our algorithm. So when we calculate all the total cost, we are going to take the first n elements from, actually is the max total nodes that are as the smaller total cost. So let's try. We're going to change also. In this case, we're going to use another query. This is 3. Let's try this one. That is list all 6 of Hermann's Einstein siblings in birth order, note the sex of each, and say which them. Let's try something more complex. Draw or describe textually a 3-generation family graph starting from Abraham, Einstein, and Leland. Let's try this one. I think it's more interesting. Okay, so we change in the params the technique, the graph traversal method. We are going to use this time the uniform cost search UCS. Here we go. Okay, we get the first 2. So we're starting from just 2 nodes. The node 0 is from the multivector search. And this is the second phase, the graph traversal analysis. Let's see. Actually, we get a lot of nodes, maybe too many. It's okay, 100. In this case, we have all the same information as before, the entity, the labels, the properties, and the relationship to the connected node. And here we go. We have the final answer. As you can see, he replied with a really good answer and structure. Generation 1, generation 2, generation 3, 4. Let's apply the predicate LLM. So we filter some node. Let's apply this one. We apply this. Okay, so we have the list of our relationship types. Now is asking to the LLM, okay, it choose this relationship, parent, child, and many others. So it's skipping neighbor, okay, because in this way it didn't find an embedding. Of course, this is an important point. So if you use this method, be sure that all the nodes, of course, they must have at least one embedding that represent the node, okay? Because if it doesn't find an embedding, it cannot perform calculation, the cosine similarity distance, so it's going to be skipped like now. But as you see here, it found anyways 16 neighbors for node. For each node actually found something. So initial documents 2, additional document from graph traversal 14, so not 100 like before. Total context document after the duplication 14. And here we go, we have the answer generation here. Wow, it created a really nice representation here, graphically, one branch. That's nice. So now things get really interesting, okay? With the A-star search heuristic, I really love this technique because it's really smart and advanced. And I really think this is one of the best techniques that we have here so far. If you apply also the LLM predicate, actually the A-star search heuristic is actually the technique that perform better than others. When I say perform better, it means it's getting really specific and you don't waste a lot of token to get the answer also for a really complex query. So let's understand how it works. What if we could combine the optimality guarantees of uniform cost search that you already saw with the power of directly targeting our query intent? So it means that just doesn't calculate the cost between the nodes, but also apply another component that represent the cosine distance between the node and the query, the initial query. So we have two components, hn, that is the same as before, plus gn. We just add a new component to calculate the total cost, as you can see here, jn plus hn. So in this way, we get a better representation of the semantic structure. While UCS discovers node in order of increasing semantic distance from your starting point, A-star search goes one step further by incorporating knowledge about your destination to the original query itself. So actually introduce the destination, okay? Now we use the initial query as a hypothetical destination. In other, maybe algorithm, you use different kind of destination. In our case, we just simulated that the destination is our user query. And it intelligently balances between them. So this approach transforms graph traversal from a systematic exploration into a goal-directed search, dramatically reducing the number of nodes that need to be elaborated while maintaining the guarantee that you will find the most relevant information via the semantically shortest path. Let's talk about the bias toward the query proximity. By adding hn to our cost calculation, nodes that are both structurally close with low G and semantically close to the query, low H, get prioritized first. So this means we discover the most relevant information earlier in the traversal process. There is also optimality preservation because our heuristic never overestimate the true cost to go. So going back to the code, if we open the A-star search, heuristic actually basically is identical to uniform cost search UCS, but we just add one component. And here we go with get from traversal. Where is it? Traversal graph. So we start the same with traverse graph, all the same, and we perform A-star. Let's see what changed. It's, as you can see here, the queue is the same. We create the metadata as the same way. We get the G-score, but also we calculate the H-star. So the H-star we calculate with this function, heuristic, that, and we are going to sum. We're going to calculate the F-score, that is G-score plus H-score. Let's see this heuristic function, and we have the node embedding and the query embedding. We are going to calculate just cosine distance between. And here we go, everything remains the same. So we are going to have heap q, and then we push inside also the open set F-score node ID and start from 0. And for each iteration, we are going to calculate the total cost. So the edge cost is going to be calculate cosine distance, and the G-score is going to be the edge cost plus G-score. Okay. And here we go. This is also important because actually in this part, if the tentative G-score is lower than the G-score for that neighbor ID that we stored before, it means that this is the best path. But if it's the same or bigger, it means that we already got the best path before, so we skip this step. Let's see how it works. So let's set directly the A-star element with the predicate point. Go. We use the same queries, initial documents, list of the labels of the relationship types. Here we go. It chooses just 7. Get just the same. I think the result is almost the same because we cut from 100 nodes. Maybe on the top we get better nodes than before. So the difference is that now the semantic similarity is aligned with the user query. So we expect that the better node on the top of the queue, we have a better node than the UCS. And we go with this node, and great, we have another answer. Maybe it's much structured, as you can see here, but it's difficult to see any difference because they're quite similar technique, but we also got a good answer. So this is the last technique we analyze in this tutorial, and it's called beam search over the graph. This technique actually explores the neighbor layer by layer, like BFS, but at each depth only keeps the top W highest scoring nodes, the beam, we call the beam, based on a chosen scoring function. So this lets you focus computational effort on the promising paths while bounding memory and latency, so at the cost of potentially pruning routes that could lead to valuable nodes deeper down. So the core concept is that layered expansion with the selective pruning. Think of the beam search as a carefully orchestrated exploration strategy. At each layer or depth in the graph, the algorithm first expands all the current candidate, okay? Like BFS, it explores all the neighbors. So it starts with the depth 1 and depth 2. It doesn't follow the path, but it goes by layer. It evaluates how promising each newly discovered node is using semantic similarity at the same way of UCS, but it keeps only the top key most promising candidate, discarding the rest permanently. Actually, we are putting together all concepts that you already saw before. And we also use the LLM predicate filter for this. So let's understand how the class works. Actually, the structure is the same. Everything is the same. We're just going to evaluate the algorithm for the beam search. We start from traverse graph, the same, and we perform the beam search. Let's see what happened here. We're going to store the beam search data structures. That's actually what is visited and discovered node. The current beam, and actually it starts with the seed nodes, and we are going to change it through the iteration, and the node scores track the node scores for the final results. Initialize the beam here with starting nodes, score 1 for seeds and depth 0. And we get the embedding for all the starting nodes. And here we have the beam search traversal layer by layer. So we start for depth. We start from 0, 1, 2, and we reach the max depth. That is our parameter. And we collect all the candidates for the next layer. Okay. We process each node in current beam. So we get all this from the current beam. We get all these variables here, the beam node ID, score, depth, parent, and we add the current beam node to discover node if it's not already added, and if the actually skip seed node as they are already in the relevant docs, okay, because the beam depth is 0, is the initial node. We get the node metadata with the actual score. And all the other, of course, we skip dimensions as before. We get the node embedding, all the neighbors. We will get all the neighbors here at the same way of the previous algorithm. And we get all the embeddings for all the neighbor, okay, with this function. In this loop, we calculate the score for each neighbor. We calculate the cosine similarity, and we add the candidates for the next layer, okay? Here we course by the score. Descending, actually higher is better, so we reverse through. And we keep only top beam with candidates, okay? So we cut with the beam width to get only the first, for example, 10 nodes that we use for the final answer. And here we prepare for the next beam. Already set in params. Beam search, we add also the predicate LLM filter. And done, query.py. Okay. We get the node in the beam score order, waiting for the answer. Here we go. We got a beautiful answer. And this is the end of our journey. So congratulations, you have just completed really comprehensive tutorial on hybrid knowledge graph RAG system. As you saw, you learn a lot of things about different techniques to traverse the graph. So we explored actually pretty revolutionary approach that goes far beyond the traditional vector similarity search by combining the semantic power of embeddings with the structural intelligence of graph databases. So I hope this tutorial has opened new possibilities for your AI projects and inspired you to explore the fascinating intersection of graph databases and vector embedding. Be free to explore, be free to modify the script, to integrate your intuitions, to apply, for example, some evaluation technique, to compare different approaches, and you choose the best one that optimizes in the best way possible Until the next time, keep building amazing things. Don't forget to subscribe to the Gradient Path for more AI tutorials and let me know in the comments what you'd like to see next. So, see you in the next tutorial.